Hello everyone. Today we're going to continue our conversations of stress, moving on to this concept of shear stress. From last time, as a reminder where we're at, what we had looked at was if I had any kind of cylinder or structural member that I was putting under some kind of axial loading, meaning it was either in tension or compression, so some force P. What we could do is we could analyze what was going on in the interior of this member, some kind of random cross section. If I were to blow it up and see what's going on inside here, I have this force P, and I'm resisting this force P all across this cross section. And this was this idea of stress, where it's evenly distributed across that cross section. We called that sigma, acting across this cross sectional area, and we defined this sigma to be equal to the total force evenly distributed across that area. So we called that either axial stress or average normal stress. Now what we're going to talk about is if we take the load and instead of having it perpendicular to the cross section, we're going to have it parallel to the cross section. So I'm going to draw the exact same cylinder I just drew a second ago. The only difference is here, this time I'm going to have a shearing force, which we designate with a V. And you can think about these being separated by some microscopic distance apart from each other, almost like a pair of scissors or something. So if I were to, once again, just look at one half or the other, I'll look at the right hand side since that's what I looked at last time. It's the same idea. Here I would only have one of those shearing forces. The other shear force would go with the other side. So to resist this shear, what I am in essence saying is I have all evenly distributed across this cross section. What I have are all of these stress, right? So this whole thing would represent a stress that is parallel to the cross section. And if we should now go ahead and define that, we call that a shear stress. So let's define shear stress, and we're going to designate shear stress with the Greek letter tau. And we're going to say that this is the stress that is parallel to the surface. And in equation form, it'll look very similar to what we did with our average normal or axial stress, or tau is equal to V over A, our second equation in this class. And of course, what this represents, our V is our shear force. That's something that you would pull from the shear and moment diagram, or if it isn't given you directly, and we're dividing it by our sheared area. Alright, so let's look at an example of how we would use this new concept. And I tried to find an example that would use both this new concept as well as our old one. So let's take a look. So here's what our example is going to look like. We're basically going to have some kind of member. I think I'd said that it was actually a wood member because I am using some material properties out of the back of the book. We're going to say that this wood member is cut at a 30-degree angle and then glued back together. So in essence, we have this plane that we're going to be looking at, and we're going to apply a force of 5 kilonewtons in tension on this member. Something like that. We also need to know some dimensions of this member, so we're going to say that this is 10 millimeters as far as a depth. And if I were to look at a cross section, what I would see is that it is 8 millimeters into the page. So this would still be the 10 millimeter side. That's my cross section. Something like that. All right, so let me put what is given and what we need to find. So given So what's given is for the two parts cut and glued at an angle, what we would like to find is the average normal stress and the shear stress at that cut or on that surface. So the way I would start with this is a free body diagram, just looking at, and you could look at either side. I'm going to look at the right hand side. If I were just to draw the right hand side, I see my cut over here with the 30 degrees. I'm applying this load of 5 kilonewtons. I know that this is a 30-degree angle. Now, what's going on the surface to resist this 5 kilonewton load? There's two forces. One is your axial force, your average normal, which is perpendicular to the surface, and we said last time we're calling it P. And then I also have a shearing force, which we're designating now as V. Now, those two forces would be perpendicular to each other because one is perpendicular to the surface, the other one's parallel to the surface, so by nature they have to be perpendicular. And I know my direction for those have to be resisting this 5 kilonewton load. So I know that they're both going to have an X component that needs to be pointing to the left, so I knew that the P had to be pointing away, and also know it's in tension, and the shear force has to be pointing down and to the left. After I have this part, I can go into my statics, and what I can start with is some of the forces in the y direction equal 0. And that means this axial force P in the y direction minus my shearing force in the y direction is equal to 0. So to get them in the y direction, I have P cosine theta, and I'm going to move that Vy to the other side, and that's V sine theta. Hopefully okay with why one is cosine and one is sine. It's because they're 90 degrees to each other. If you're struggling with that, revisit your trig functions and map it out, and draw your triangles, whatever you need to do to convince yourself. So if I divide both sides by cosine, I end up with V sine over cosine is tangent, so I get V tangent theta. Same idea in the x direction. If we said sum of the forces in the x direction equals 0, I have this 5 kilonewton force pulling to the right minus P, now we're talking about the sine of theta, minus V cosine theta is equal to 0. Basically we have two equations, two unknowns, are P and V, so that's kind of what I'm doing here with these. So I have to have some way to solve it. What I'm choosing to do is I'm going to sub in my P into this last equation, and I'm going to solve for my shear force V in terms of the angle theta. So what I end up with is V, and you could do the algebra yourself. I'm going to jump ahead and assume you can do the algebra, times sine theta tangent theta plus cosine theta is equal to 5 kilonewtons. And I left it in this generic form that way in case you have a problem that does have some kind of cut like this and you're looking for both an axial force and a shearing force. You could jump basically right to this equation since it's already been derived for you. From here I can just plug in my thetas, solve for V. If I do that, I end up with a shear force of 4,330 newtons. Plug that back into my my P is equal to V tan theta, and I end up with a P that's equal to 2,500 newtons. If you're just watching this video, perhaps it'd be a good idea to pause it and make sure and verify these results. Well, actually, I don't want to do that. I almost put a box around it, but really, these are not the final answers. These are just the forces, and we're not asked to find the forces, we're asked to find the stresses at this cut. So the next step is that we have to divide these forces by the cross-sectional area. So a common mistake here would be to say, well, I have an area that is, I have a cross-section that is 10 by 8, so the cross-sectional area must be 80. But that would be incorrect because the cross-section actually is all along this little section, right? So if we want to look at what our area actually is, looking at I'm going to do my best to draw a 3D of this thing. This could get a little ugly, but we'll see what happens. Alright, so with a 10 millimeter side and 8 millimeter into the page, this is my cross-sectional area. So I need to figure out how to find that. The key would be this overall length right here, right? Well, I can make that into a triangle and figure it out because I know that's 30 degrees. I know that that length must be equal to 10 over sine of 30. Once again, if you're struggling with your trig, go ahead and map it out and verify it for yourself. So what that means is my cross-sectional area for this guy is going to be the 8 millimeters times the 10 millimeters over the sine of 30 degrees, and that gives me like 160 square millimeters. So last but not least, now I can find my stresses. My average normal or axial stress, which you said was P over A, would be equal to this 2,500 newtons over 160 millimeters squared, giving me something like 15.63 megapascals. And for my shearing force, so it is V over A. I have this 4,330 newton shearing force, cross-sectional area of 160 millimeters squared, giving me something like 27.06 megapascals. So that's kind of how the general process. That's about as bad as they get for this part. When we talk about this average normal stress in our average shear stress across this cross section. Hope that video was helpful, and I'll look forward to talking to y'all soon. Thanks.